With this. Yeah, I'm seeing a bunch of people now whom I didn't see before because I think I increased the screen size now. Okay, so you want me to test the sharing? Are you able to see now?
Gaurav, you're muted. Yes, we can see.
Am I muted?
No. Gaurav is
Okay.
muted.
Yeah. Okay. All right.
Yeah, we can see the slides.
But I'm not able to see my image. How come?
Oh,
Something happened. So what do I do? Suppose
can you see
if
the
I
video below, like the audio video thing? You can.
I don't see the audio video screen because I'm sharing. What if I close this?
Or instead of minimizing,
Wait.
click on bit, the button in between, the
Right?
next to minimize.
No, wait.
I think,
Sharing is
yeah, if you do Control F, I
hold
think,
on. Wait, did I go away?
no.
Krishna, we can't see you for some reason.
Yeah, that's
Yeah.
Your
No,
off.
let me. Yeah, okay, now. Okay, I don't know. Somehow the video got cut.
Yeah, I think if you
Now,
do
yeah. So
maximize
now I'll do the sharing. I'll do the sharing again.
Sure.
Yes. Yes. So am I okay now?
Yeah. If you
All
do
right.
Control F, I think it will go to full screen.
Okay.
Then he won't be able to see himself.
Correct.
Oh, it does come on the side, right? I don't know.
I mean, this is fine too. We can read.
Okay, sure.
Yeah.
So
If you
you
can
want to
read this,
explain?
that's okay.
Yeah.
Okay.
Atul, you're on.
Yeah. Good evening, everyone.
Okay.
Yeah, welcome to the Ramanujan special lecture of special functions in and number theory seminar. So we are going to start with a well-known speaker, Professor Krishnaswami Alladi from University of Florida, Gainesville. Many of you know Professor Alladi. He is instrumental in instituting this Shastra Ramanujan Prize since many years, and since 2005, to be precise. He has also worked in partition theory, analytic number theory, combinatorics in general, and seamlessly goes between analytic number theory and combinatorics. Today, he will be talking on second order duality between prime factors and primes in arithmetic progression. Over to you, Professor Alladi.
Thanks, first of all, to um, Gaurav for first contacting me and inviting me. And thank you also, Atul, for organizing this seminar with Gaurav and for your very kind words of introduction. Yeah, I think it's wonderful that you have this seminar out of India as a joint effort between the groups in Delhi and IIT Gandhinagar and elsewhere. So this is really wonderful. I'm very happy to give this lecture, the Ramanujan lecture. So this will be in analytic number theory, and it's joint work with my PhD student, Jason Johnson, who just defended his thesis in December, early December. Before I left for India, he finished his thesis defense. So it really, and for those of you who have heard this talk before, for example, Atul Dixit, because I was in IIT Gandhinagar as a result of his gracious invitation recently. So please bear with me if there is repetition in what I say. Okay, so as I said, this says second order duality. So I first have to go back and explain the background to you. So this is a rough overview of the talk. Right away, I will, in the introduction, state the main result so that you know exactly what the talk is about. And then we'll, as background, I'll also talk about Mobius function. And the key thing here is the discussion of the number of prime factors, the study of which was originated by Hardy and Ramanujan. And then we'll do some analytic versions of the study of mu of n, omega n. Omega n is the number of distinct prime factors. Now, the key thing here is the comparison of the study between the sizes and the distribution of the largest prime factor and the second largest prime factor. In particular, we'll need to prove a certain uniform distribution result, which will come out of the prime number theorem for arithmetic progressions, and that sets up the proof of the main theorem. And then I will go on to talk about more general situations, as well as more recent work on analogs of the results that we have in algebraic number theory, as well as Q analogs. Okay, all right. So that's the overview of the talk. Okay, so let me begin with two very famous statements, two very famous results of Edmund Landau. The first of this is that if you sum the Mobius function from 1 to x, this is little o of x. So what is the Mobius function? It's 0 for numbers which are non-square free, that is if p squared divides n. And for numbers which are square free, namely products of distinct primes, it is -1 to the number of prime factors. So the square free numbers are about 6 over pi squared in density among the integers. So a good proportion of the integers are square free. And what this result says is that asymptotically, half the time, the square free numbers have an odd number of prime factors, and half the time they have an even number of prime factors. So that's the little o of x. And the next result, which is also equally impressive, is that if you sum the series mu of n over n from 1 to infinity, this is value 0. And what Landau showed was that both of these results are elementarily equivalent to the prime number theorem. By elementarily equivalent, we mean that if you assume any one of these two results, you can very quickly derive the prime number theorem in its simple form, pi of x asymptotic to x over log x. And conversely, if you assume pi of x is asymptotic to x over log x, then you can get both of these results without any difficulty, and you don't need any complex variables to get these. So that's what we mean by elementarily equivalent. And of course, the other point is that if you have the strong form of the prime number theorem, that is with its explicit error terms and so on, you can get corresponding error terms, corresponding bounds for m of x and corresponding error term for the tail of the series mu n over n from x to infinity. Okay. All right. So now here is, I want to start off straight away with duality, which I observed in actually 1976. A paper was published in 1977 in the Journal of Number Theory, and this was one of the main features of my thesis, the consequence of these two identities. So what this says is, you choose any function, f on the primes. Now you sum mu d, f of the smallest prime factor of d, over divisors of n which are at least 2. We don't include 1 because there's no smallest or largest prime factor for 1. It's just a formality to set the largest prime factor of 1 to be 1. And then, so what we do is we just define f of 1 to be 0. So if you want to do that, then you can take a sum over all divisors. But the key point is that when you sum this Mobius function, f of the smallest prime factor of d, you end up getting minus f of the largest prime factor of n. And this can be reversed. So that's identity 4. Summation mu d f of the largest prime factor of d is minus f of the smallest prime factor of n. So these are not difficult to prove, but the key thing is to make such an observation, because this is very fundamental. I mean, this is right at the foundations of the subject. So obviously, this should have some important implications. So let me straight away give you a striking result that comes out of this. But of course, the proof of this result requires analysis involving prime number theorem and various things. So so one consequence is that if you take any bounded function on the primes, and let us say the function has an average on the sequence of largest prime factors, which means summation f of p of n, 1 up to x, divided by x, as x goes to infinity, has a limit c. Then the result is that the sum of the Mobius function, f of p of n, but now with the smallest prime factor of n divided by n from 2 to infinity, gives you minus c, and vice versa. So from 6 you get 5, and from 5 you get 6. Okay, so this is a result that comes out of this duality. As I said, the proof of this result is involves analytic techniques. Okay. Now, we think of this as a surprising generalization of Landau's result. Why? Because what I do is I can take Landau's result and write it as summation 2 to infinity is minus 1. Because if I remove the first term, 1 to infinity, I remove the first term, mu of 1 is 1. I've removed the 1, and that sum is 0. So once I remove the 1, this sum is minus 1. So what I do is I go back to this situation. And what if I choose f to be the simple constant function 1 on the primes? Then obviously the average over the largest prime factor exists, and it is 1. So C is 1. And therefore in 6, you will get minus 1, which is precisely this result of Landau. So Landau's result is just the very special case of this equality, the equivalence of 5 and 6, by just choosing f of 1 to be 1 on the primes. Okay, but now let me give you another very striking application. We all know the prime number theorem for arithmetic progressions, which states that if I'm given a modulus k and you choose any of the residue classes L, which are relatively prime to k, then the sequence of prime numbers is uniformly distributed in the reduced residue classes modulo k. Now, what if instead of the sequence of primes, I write down the sequence of largest prime factors? So the sequence of largest prime factors is actually a sequence of primes, but with repetition. So for example, the first term is 2, the second term is 3. Now you come to the integer 4, the largest prime factor is 2. So you write 2 again. Then you have 5. And then for 6, the largest prime factor is 3. So 3 comes again. So it's really the sequence of primes with a repetition introduced. But the point is that one can show, and this is a theorem I proved in my 1977 paper, that this repetition, by looking at the sequence of largest prime factors, does not destroy uniform distribution. So in other words, the sequence of largest prime factors is uniformly distributed in the reduced residue classes L mod k. So what does that mean in our situation? Suppose I choose f to be fkl, the characteristic function of primes in an arithmetic progression L mod k. Then we go back and we now say that since I know that the sequence of largest prime factors is uniformly distributed in the reduced residue classes, what it means is that if I choose this f to be the characteristic function of the primes in those residue classes, this average will exist. And that average C will be 1 over phi of k, which means the Mobius series will now converge to minus 1 over phi of k, but this will be the same value, minus 1 over phi of k, for all residue classes L. But now we are looking at the smallest prime factor being L mod k. So this is actually quite surprising, because what is really happening is, if you do not have the condition Pfn congruent to L mod k, and you look at Landau's result, summation mu of n over n from 2 to infinity in 8, then you get minus 1. So what we are doing is, we are now taken that convergent Landau series, mu of n over n from 2 to infinity, which is equal to minus 1, and we have sliced it into phi of k subseries. But all the subseries are converging to the same value. I don't know, at least at that time when I proved this, I went to my thesis advisor, Professor Strauss, and I said, you can take divergent series, because in a divergent series, let's say positive term, it's a long-term phenomena. So you can slice it into asymptotically equal subseries. Like you take, for example, the harmonic series for which up to x is the logarithm. You take the subseries of odd numbers, 1 over 3, 1 over 5, etc. You're going to get approximately log x over 2, because it's a long-term phenomenon. But for convergent series, it's very sensitive to the initial values. So if you start slicing, there is no guarantee that you are going to get an equal value. I mean, suppose I take a convergent series for log 2, and I ask you, slice it into 10 subseries, each of them equal to log 2 over 10. Of course, a slicing exists, but can you construct such a slicing? So here, we have done such a slicing in a very natural way. So I think this, as far as I know, this is the first example of such a slicing of a convergent series, but we are doing it using the smallest prime factor. So this was a striking result. And in fact, when I showed this to my thesis advisor, he said, you know, this is your thesis, right? A variety of results related to this, and that's your thesis. Okay, so anyway, so this is very nice, and this is related to the prime number theorem for arithmetic progressions, just as Landau's result is related to the prime number theorem. Now, recently, this particular result 8 has attracted a lot of attention. It's really coming out of a seminar that I gave to Ken Ono's group when he was at Emory, and Ken turned towards the students and said, in particular to Madeline Locus-Darcy, and said that you should generalize this in the setting of algebraic number theory, which she did in 2017. And I'll come to that towards the end of the lecture. And further results were established by others who interacted with Ken, Sweeting and Wu, Corral, McDonald Sa, Wang, and others. And also Ono himself, along with Schneider and Wagner, have discussed Q analogs of this result. Okay, so I'll get to all that towards the end of the talk. All right, so now I want to mention the motivation for this paper. So in that same 1977 paper, I studied higher order dualities. So let us denote by pkn capital and pkn smaller case, the kth largest and kth smallest prime factors of an integer. And if n has k distinct prime factors, okay, if n has fewer than k distinct prime factors, then these numbers are just set equal to 1. And let omega n denote the number of distinct prime factors of n. Now, this is a Ramanujan lecture, so I want to, of course, emphasize that even though prime numbers have been discussed since Greek antiquity, the first systematic discussion of the asymptotic behavior of the number of prime factors is to the seminal paper of Hardy and Ramanujan in 1917 on round numbers. Okay, so we'll use a specific result of Hardy Ramanujan later on. So this higher order duality identities that I proved are that summation mu of d, f of the kth largest prime factor of d, summed over d bigger than 1, I'll tell you what the star is in a moment, turns out to be minus 1 to the k, omega n minus 1 choose k minus 1, f of the smallest prime factor. So the duality is not between the kth largest prime factor and the kth smallest prime factor. It is between first you have an identity connecting the kth largest prime factor with the smallest prime factor. When you reverse, you have an identity connecting the kth smallest prime factor with the largest prime factor. That is how the duality exhibits itself. So it's a perfect duality in the case k equal to 1. Now the star means the summation is over numbers for which the number of distinct prime, if the number of distinct prime factors is less than k, we just put the summation equal to 0. But that also is obvious from the right-hand side, because if omega n is less than k, that binomial coefficient becomes 0 anyway. So this is the pair of identities. So my goal here is to discuss consequences of this when k is 2. And this is considerably more complicated than the k equal to 1 situation. So let me recast these two duality identities using Mobius inversion. So if I do Mobius inversion, the two duality identities become 11 and 12. And as I said, we're going to focus on the case k equal to 2, especially identity number 12. So I've rewritten identity number 12 here for you. So this is summation mu of d, d dividing n, d bigger than 1, mu of d times omega d minus 1, right? Because k is 2. So omega d minus 1 choose k minus 1 is just simply omega d minus 1. And with f of the smallest prime factor, and that is f of the second smallest prime factor. Remember, in that duality, you don't have a minus sign now, because there you have a minus 1 to the k, and now k is 2. So previously, we had a minus f of the smallest and largest. Okay, so now I have just f of the second smallest. So what are the results that we have now? So first point is, analogous to Landau's result on mu of n over n, we can show summation mu of n, omega n divided by n from 1 to infinity is 0. This is more complicated to prove. And obviously, in this particular case, since the number of prime factors of 1 is 0, if I eliminate the first term, I will get summation mu of n omega n divided by n from 2 to infinity is still 0. Previously, when I eliminated the first term, I got a minus 1 on the right-hand side. Now I still have 0. But what is really nice is we do the following. Just as previously we had the sequence of largest prime factors is uniformly distributed in the reduced residue classes, we can now show that the sequence of second largest prime factors is uniformly distributed in the reduced residue class. But this result is more difficult to prove. But once we have this, by choosing f to be fkl, that is the characteristic function of primes in an arithmetic progression, we can then show that summation mu of n omega n from 2 to infinity, and with this condition, p of n congruent to L mod k is actually 0, which means that we have taken this convergent series in 15 and sliced it into phi of k equal valued subseries, and obviously all the equal values will be equal to 0. Okay, so that's what it'll be. All right, so hold on. Okay. Yeah, so that value will be 0. All right, so this is the main result of the paper. And of course, we will prove quantitative versions of this result. And we have just submitted it to the archive and also submitted this for publication. So this is with my PhD student, Jason Johnson. Okay, now let me point out some key differences between first and second order dualities. A key computational tool in the first order duality is psi of xy, the number of integers up to x, all of whose prime factors are less than or equal to y. So these integers are called integers with sometimes called smooth numbers. That is, they have integers devoid of large prime factors. And they are a very important collection of numbers. They come up in problems involving, algorithms for primality testing, factoring of large numbers, in many situations. Psi of xy is a very fundamental function. Now, the key point is that this psi of xy is small, very small compared to x when alpha is large. Alpha is the ratio of logarithms of x and y, or you think of y as x to the power 1 over alpha. So as y starts falling down from x, and let's say square root of x, cube root of x, fourth root of x, and so on, alpha root of x, the size of psi of xy is no bigger than x e to the minus alpha over 2. So it's an exponential decay. Now, in contrast, psi 2 of xy, the number of integers up to x for which the second largest prime factor is less than or equal to y, even though this becomes small in comparison to x, little o of x, in comparison with x, when alpha is large, it is not that small. In fact, you can quickly see that it can never really get smaller than x over log x. Why? Because the smallest value of psi 2 of xy is obviously when the second largest prime factor is 2. But all numbers of the form 2p, where p is a prime and 2p is less than or equal to x, will obviously have second largest prime factor 2. And the number of these numbers is the number of primes up to x over 2, and that's of the order of magnitude x over log x. Therefore, this psi 2 of xy is never really that small. It is going to be little o of x for our purposes, but never really that small. So what we want is some sort of a strong result on psi 2, which I will state in a moment. Now, there is a second difference also that comes up, and that is the function m of x, which is small, as shown in 19, which comes from the strong form of the prime number theorem, actually changes sign infinitely often. This is not very difficult to prove. This comes out of a certain result of Edmund Landau, a different result of Landau, also called Landau's theorem, which relates to Dirichlet series, okay, with coefficients which are of the same sign. But on the other hand, this sum mu of n omega n less than or equal to x actually turns out to be asymptotic to constant times x over log squared x, and therefore it does not change sign infinitely often. So the analysis of m omega, and especially because it's not that small, is more difficult. Okay, so now let us begin with the Mobius function and the number of prime factors. So how do we prove that summation mu n omega n less than or equal to x is little o of x? So what we do is we take that omega and we write this as a double sum by simply writing omega summation 1p dividing n. Now we reverse the order of summation as we always do. So now it's a sum over primes less than or equal to x. And now the inner sum is a sum over integers up to x, which are 0 mod p. So you write those numbers of the form m times p, but obviously m and p have to be relatively prime because otherwise the Mobius function will become 0. So the inner sum in 21 is really a sum mu of m over numbers m which are no bigger than x over p, which are relatively prime to p. So here I introduce a function called m superscript p of x, as in 23, which is the sum of the Mobius function over numbers up to x, which are relatively prime to a single prime p. So in other words, they just miss a single prime factor p. So that function now comes into 22, and the inner sum in the middle can be written as mp of x over p. And now, of course, you have to sum this over all primes less than or equal to x. Now, the key point here is that using the Perron integral method, which is the method that one would use to get bounds for m of x, using zero-free regions of the Riemann zeta function and bounds for zeta in those regions, you can actually show that no matter what p is, there is just a universal constant c1 and a universal implicit constant in the less than, such that mp of x is no more than x e to the minus c1 square root log x. So this is not difficult to show. A single prime does not cause a problem. So once we have that, what we have to do is we have to go into this summation at the right-hand side of 22, and I have to split it as p less than or equal to t and p greater than or equal to t, okay, as is written in this next slide. But the p less than or equal to t can be easily controlled, but the p bigger than or equal to t is what causes some problem, because the p can get close to x, and then therefore the x over p is not that small, right? So what you do is you break it up into x to x over 2, x over 2 to x over 3, x over 3 to x over 4, and each of these intervals you have to carefully estimate it. And in the end, you can show, and I'm not going through the details here, that this sum is no more than x over log x in size. So this is little o of x. All right. Now, the next thing is a standard trick that is there in number theory. You replace the same sum mu of n omega n, but now introduce a weight, which is the fractional part of x over n. And this is a method that goes back to Axer. And I'll get to Axer's method later when I prove the main result. But here I'm just simply saying that by Axer's result, you can show that this is also little o of x. But notice that I have paid a price in introducing the fractional part. Previously, I had x over log x, but now I end up getting x over square root log x at the bottom and a square root log x at the top. But it doesn't matter. This is still little o of x. But now the next thing is, since I have the fractional part, what happens if I have the integral part? Well, the nice thing is that this sum mu d omega d, which when you take d dividing n, this is really the negative of the characteristic function of the set of prime powers. So it's quite a nice, well-behaved function. So that means the summation mu of n omega n integral part of x over n is now written as this double sum. So when I reverse it, I end up getting the negative of the characteristic function of the prime powers. And that, of course, by the prime number theorem, is minus x over log x plus O of x over log squared x. So that means if I add the fractional part and the integral part, okay, I have something for the integral part, I have something for the fractional part. If I add these two, I will get summation mu of n omega n times x over n. And that sum will be the sum of these little o of x terms. And you have to obviously take the largest of the little o of x terms, and the largest of the little o of x terms is this root log x over log x. And what I've done here is I have canceled the x throughout. So previously I had an x over n, I've canceled the x. And this proves that the partial sums mu and omega n over n less than or equal to x, is little o of x with an explicit bound given in 26. And consequently, as x goes to infinity, this sum is 0. So this is one way of proving that this sum mu of n omega n is actually 0. Okay, so I've described that here. I already explained it. Now, let me mention the analytic approach to mu n omega n, which is rather nice. So what is this analytic approach? So we go back to considering complex powers of the Riemann zeta function. So let's look at zeta s to the z. And the first person to seriously study this was Selberg in a very fundamental paper in 1954 that appeared in the Indian Mathematical Society. I don't want to get into the history of this. It's actually got a very interesting history. So this paper is actually a note on a result of L.G. Sathe, where Sathe solved Hardy's problem of determining asymptotically the number of integers with a fixed number of prime factors, k, but that k can vary. So he got uniform estimates. He did that by grueling induction method, because induction gets complicated as k varies. And Selberg showed how nicely you can do it analytically. So that's how Selberg was interested in this. Okay, so Selberg refers to this as the generalized divisor function. Why generalized divisor? Because if I put z equal to 2, that is zeta squared, then this is really the generating function for the ordinary divisor function, right? So it's d of n over n to the s. So Selberg showed that this summation dz of n is x log x to the z minus 1 over gamma z plus an error term that depends upon r, where what r is that you choose complex numbers inside a circle of radius r, and this estimate is uniform for all such complex numbers. So you get x log x to the z minus 2. So it's 1 logarithm power lower. So when I put z equal to 2, you get the main term in the divisor function, which is x log x, and of course gamma 2 is 1. And we all know that the Dirichlet initial result is that the sum of the divisor function up to x is x log x plus 2 gamma minus 1 of x plus O square root of x, and you see that x log x here. All right, so but now the problem is that when you have zeta s to the z, you have a branch point. It's no longer a pole at s equal to 1. So you've got to go around the branch point, and what Silberg noticed was that leads to, if you use the Perron integral method, this leads to a Hankel contour when you do some transformations, and it is due to the presence of the Hankel contour that you end up getting the gamma function in the denominator. Okay, so that's why the gamma comes in, due to the Hankel contour. All right, now Silberg actually considered more general sums of the type, more general Dirichlet generating functions of the type zeta s to the z times h of s, where h is an analytic function and real part s bigger than half. So what is of relevance to us here is we are looking at s minus z of x, which is summation mu of n z to the omega of n, all right? And therefore, if you look at the Dirichlet generating function for that, I've written that down in 31, it just gives you a beautiful Euler product, 1 minus z to the power s. And now that Euler product is related to the zeta function to the power minus z. So you write it as zeta function to the power minus z multiplied by a gs of z. And the gs of z is explicitly given to you in 33. But this, what it does is that this gs of z becomes analytic in real part s bigger than half. So this fits into the Silberg program of having that h of s being analytic in real part s bigger than half. So you can use the Silberg method involving Hankel contours to evaluate summation mu of n z to the omega n. And when you do that, the result that you get is that this s minus z of x is what Silberg previously had. I've now replaced z by minus z because because of the Mobius function. You see, I'm looking at this sum. It's not just z to the omega n, but mu n z to the omega n, which is like minus z to the omega n. So that's where the minus z comes in. And so I have the same Silberg result, but as you can notice, I have a g of 1z brought in because of this extra factor. But the error term is the same. Now, many years later, the French mathematician Hubert Delange noticed that the same method of Silberg can also be extended to consider functions of the type zeta s to the z multiplied by a power of the positive integral power of the logarithm. Now, this is not surprising because e to the zeta s to the z itself is e to the z log zeta z, as you can see in the third bullet. And it is that log zeta z which is causing the branch point. So what Delange is saying is, since you're anyway able to deal with zeta s to the z, why not I put in a more general expression by multiplying by powers of the logarithm also, and you can deal with the same thing using the Silberg method. But of course, you've got to be a little bit more careful with regard to error terms because now you're looking at not just zero for reasons, but bounds for the logarithm. All right, so that is the Silberg-Delange method, and there is a very thorough account of it in Tenenbaum's probabilistic and analytic number theory, and Tenenbaum actually has improved the original results of Silberg-Delange. Okay, but now, what is the relevance here? The relevance is that this m omega x can now be considered as d dz of s minus z of x at z equal to 1, right? Because go back to s minus z of x, which is here. Formally take the derivative of this with respect to z. The omega n comes down. And now I put z equal to 1, you get summation mu n omega n. So this mu n omega n can be viewed as the derivative of s minus z of x at z equal to 1. Now, what you can do formally is you can take this asymptotic formula for s z of x, that is in equation 34. Just for now, ignore the error term. Just look at the main term. And let us say I just differentiate the main term. When I and assume that that differentiation will give the asymptotic for m omega of x. So that's what is given in 37. You'll then end up getting m omega of x is asymptotic to a constant x over log squared x. Okay, but all this can be established rigorously by the Silberg-Delange method. So you first heuristically guess the size, and you can get this by the Silberg-Delange method. And consequently, you can also do the summation mu and omega n and you end up getting that mu n, this m omega of x is x log squared x, and this little n omega is now also going to be better than the result that we had before. So I pointed out my result on mu n omega n to Tenenbaum, and in his response in a letter, he said, Krishna, you can actually get a series representation for this in decreasing powers of log x, just as you have a series representation for pi of x using the logarithmic integral of x. You can write it as x over log x plus constant x over log squared plus constant x over log cube. You can get something similar here. But these results, neither the results nor this analytic method is will be needed or will be used in our general result, because there are many things fail. All right. So this is just to give you an idea of what the analytic method yields. Okay, so I mentioned this fundamental counting function of De Bruijn, which is investigated by De Bruijn, which is the number of integers whose largest prime factor is no bigger than y. De Bruijn established, actually, Tenenbaum, by polishing up De Bruijn, established x e to the alpha over 2 uniformly in this region. De Bruijn had x e to the minus c alpha, okay, with an unspecified c. And then he showed the second one, which is stronger and which is valid for y bigger than or equal to log squared x. But now the real asymptotic behavior is as follows. Psi of xy is actually asymptotic to x times rho of alpha in this range, where rho of alpha satisfies this integral differential equation. And De Bruijn actually analyzed rho of alpha asymptotically, another paper published in an Indian journal, by using the saddle point method, and that's asymptotics is given in 50. Actually, it's not asymptotic because it's asymptotic only in the exponent, which means it's asymptotic for the logarithm of rho of alpha. All right. Now, my comment about the second largest prime factor. You see, the largest prime factor of a number is uniquely defined. The second largest prime factor has two possible definitions. What you can do is you can take the integer n, remove the largest prime factor, and then ask what the largest prime factor, what remains is. That is one way to define a second largest prime factor. Now, in that case, the second largest prime factor of 18 is still 3. Largest prime factor is 3. But if I remove 3, I get 6, and the largest prime factor of 6 is still 3. Okay. So you end up getting that when you have a largest prime factor to repeat. Or you can define the second largest prime factor to be the largest prime factor strictly less than the first largest prime factor. So there are two definitions, and they involve the number of prime factors in a strict sense and the number of prime factors with definition, with repetition. And here we choose the definition of the second largest prime factor in the strict sense. But regardless of whether you use it in the strict sense or in the weak sense, Theorem 5 tells you that it doesn't matter which definition you use, because the number of integers up to x for which the second largest prime factor repeats is actually very small. The number of such integers is x over e to the power 1/2 square root log x log x. Now, why is this the case? This is because of De Bruijn's result. If the largest prime factor is no more than e to the half, then you get this bound in 51. So I will ignore all of those numbers. And now if the largest prime factor is large, that means bigger than that number. And if it repeats, then the number is automatically a multiple of p squared. And the number of such integers is O of x over p squared. So you have to sum x over p squared for p bigger than this. And that sum is like the tail of the x over n squared. And so you end up getting something very small anyway. So the number of integers up to x for which the largest prime factor repeats is very small. Okay. The next result that I need is, we said that the second largest prime, the psi2 of xy function is not always that small, right? But we need a quantitative result as to how large the second largest prime factor is, okay? So that is given by Theorem 6. The proof is rather complicated. So I just mentioned what the result is. So the result that we're going to use is the number of integers up to x for which the second largest prime factor is smaller than e to the root log x is no more than x over root log x. And more generally, the number of integers up to x for which the second largest prime factor is no more than t is less than x log t over log x. Okay, so this is what we're going to use. And this result is rather complicated and to prove. Tenenbaum actually has an asymptotic version of this, but he uses heavy analytic techniques. Now, the reason for doing this is that, and I'm going to skip this proof for lack of time, okay, is we want to get to, why do we want to get to the large prime factors? You see, I want to use the strong form of the prime number theorem. But to use the strong form of the prime number theorem, you don't use it when x is 100. You use it when x is asymptotically large so that you can control the error term is really small in comparison with the main term. So I need to deal with functions where the prime factors are large, or the second largest prime factor is large. That's why I have this statement which says the number of integers for which the second largest prime factor is small is negligible, or it's little o of x. Okay, so now let me go to the proof of the result that actually sets up the proof of the main theorem. So the sequence of second largest prime factors is uniformly distributed in the reduced residue classes modulo k. So that's what is in 60. I count the number of integers for which P2n is L mod k. The total number of integers is x, and I divide by phi of k, and the error is little o of x, but it's got this log x squared factor in the numerator. Okay, now how do we prove this? So the first thing we do is that we only focus, first of all, we note here that the number of positive integers for which omega n is 1 is simply the primes and the powers, and so that is O of x over log x. So that is really absorbed in this error term. So we discard integers which have 1 prime factor, all right? So we only look at integers with 2 prime factors or more, so that the second largest prime factor is well defined. And now we use a simple identity. Let S2 of xp denote the number of integers up to x for which the second largest prime factor is exactly p. So the second largest prime factor is never bigger than square root of x. So if I sum the number of such integers, which is absolute x to p, I should get all the numbers up to x except for the numbers with a single prime factor. So I should get x minus x over log x plus O of x over log squared x. So that's an actual identity in 62. Now the next thing I do is I have to look at a composition of integers with the second largest prime factor. So I look at n equal to m, write it in the form npq. So p is your second largest prime factor, okay? So q is a prime that is bigger than or equal to p. You can put strictly bigger than. And all prime factors of m must now be smaller than or equal to p. So if you write, so the exact expression for S2 of xp is of the type that I have given here, because the m now is no more than x over p squared. So that is the expression that we have in 64, all right? But the inner sum is over m, and the outer sum is over p and x. So the key thing here is to convert this sum into a sum in which the inner sum is over p. And that is what is achieved in 65. I have to rewrite this sum in terms of the second largest prime factor, and I've written it there in 65. But when you do that, the m is now an integer, all of whose prime factors are less than or equal to p, and the m is no bigger than x over pq. So that's why you get the psi function, and here are these conditions on the p. All right. So we break it up into 2 regions, the sum in 65, so that these 3 conditions actually boil down to a single condition, as is written down here for the inner sum. Now comes the key idea. The key idea is we replace the inner sum, only the inner sum, by an integral. So that integral means I'm replacing the summation psi of x over p over the primes with an integral psi of x over t dt over log t. So I'm using the strong form of the prime number theorem, motivate that to write that, and I call that sum as sigma and the integral as I. And I go through and evaluate that difference. I have to break it up for each of the 2 ranges. And the strong form of the prime number theorem, this proof also is a little complicated because you've got to really use properties of the Dieckmann function psi. You end up getting 2 expressions, the ones in 70 and 71, both of which are little o of x, provided y is chosen suitably. And the optimal choice of y in this case turns out to be e to the power 2 times log x squared. So when I do that, I get a value where I say the integral I must be x in asymptotic size. Why? Because in 72, we notice that the difference between the sum and the integral is small. But for the sum, I simply use this trick that I had. The sum is asymptotic to x. and therefore the integral must be asymptotic to x. Okay, good. Now you might say, okay, so what is the big deal in this? The big deal is the following. We do the same trick for the integers where we are now looking at the second largest prime factor is L mod k. But when you look at the second largest prime factor is L mod k, you're putting the same condition as you had before for S2 xp, but now the p is congruent to L mod k. Okay. Again, we discard all the smallness of P2 of n, only look at the largeness of P2 of n, but I can't estimate the sum. So what I do is I write an expression for this sum like I did before using the Dickmann-de Broglie function. I put this P congruent to L mod k at the bottom, and now I convert it into an integral, this time using the strong form of the prime number theorem for arithmetic progressions. So you see that 1 over phi of k expression comes out in 79. But that 79 is the same expression that I had for the integral in here with a 1 over phi of k outside. So the beauty is when you go to the integral, the 1 over phi of k just pops outside, and therefore I immediately deduce that this 1 over phi of k is, by the way, clearly that IKL is not 1 over phi of k, that is actually an I. You have to look at it carefully. So it is the old integral divided by phi of k, but the old integral I said is asymptotic to x, and consequently we prove that the numbers are the second largest prime factor is uniformly distributed with an error term as given in 81. And again, the optimal choice turns out to be 2. Yes? Did you have something? I'm sorry, I heard some voice. Okay, so that's what we get. Okay, so now
Survi, can you
somebody will mute their mic. Okay, all right. So now the next thing we do is that we look at summation mu of n omega n and over smallest prime factor congruent to L mod k, and we want to show that this is less than this quantity that is given here. So how do we do this? We choose f to be the characteristic function over the primes, and we use duality. So at this stage, the duality tells you, and here a remarkable thing takes place. So we use the duality, which is summation mu of n omega n minus 1 gives you the sum over the second largest prime factor. Remember that. But now this is equal to summation f of pd. So when you do this, you write it with Mobius inversion in the form mu of n over d f of the second largest prime factor. That is the hyperbola method. So we split it into 2 ranges, 7 and 8. 7 is over a small collection of numbers, and therefore 8 is going to be small. But when you get to 7, and that's where the key idea comes in, I'm summing the second largest prime factor over for f of the second largest prime factor, right? We proved that the second largest prime factor is uniformly distributed in L mod k. So when you go to the second largest prime factor, that sum is now of the form x over phi of k times m. Pull out the phi of k, and now you have the sum mu of m over m. And that mu of m over m is small. That is Landau's theorem. So we fall back on the strength of Landau's theorem to get an explicit upper bound. And so in the end, we are able to prove that this sum is very small. Okay, so that is the proof, but it is that technical point. Now, we come to the same thing with the fractional part of x over n. Okay, I'll finish in about 6-7 minutes. Now, for the fractional part, I mentioned that there is this trick of Axer. So I'll tell you what this trick of Axer is. You take this summation mu of n fractional x over n, split it into 2 parts, small n and large n. For the small n, you use the Hardy-Ramanujan theorem, and that sum is the first sum is bounded by an absolute value by the sum of omega n, as I've written in 91. And Hardy-Ramanujan showed that the average value of omega is log, so that's bounded by t log t. What about the large values of t? So now the n is there. I introduced this quantity m omega lkx. So the large values are now written as the sum from t to x, but each mu n omega n is now the difference between the capital M omega functions. Now you reverse the order of summation, and you end up getting the difference between the fractional parts at x over n and x over n plus 1. So I simply bound it with putting absolute values. Now the key point is this. You use the bound for m omega x lk that we have obtained previously. And that's that x log x to the 4th power over log x. That's what I established previously using duality and the hyperbola method. Now, what is the inner sum? The inner sum is no more than the total variation of the fractional part function in the interval from 1 to x over t. So the sawtooth function has total variation no more than x over t. So you get a bound involving t in the denominator. There you have a bound with t in the numerator, 91. And now you set the two equal, and the optimal choice of t is now given here in 95. And with that, the theorem 9 is proved. So that's how we end up getting the proof of theorem 9. Okay, now, finally, we got to get theorem 10. Right? So to get our main result, which is this, we use the integral part. And here a miraculous cancellation takes place. The integral part thing with duality works only with mu n omega n minus 1. So we have to separate that out, and that is equal to f for the second largest prime factor, and that is x over phi of k because of the uniform distribution result. But on the left-hand side, I have to separate it into two terms, and when I separate it into two terms, the term without the omega is my old duality. And that's in 97 is minus f of the largest prime factor of n. And for that, I already have established a uniform distribution result, and I have a minus x over phi of k. But now look at 96 and 97. In 97, I have a minus x over phi of k. In 96, so I've got a minus x over phi of k for the term mu n f of pn integral part of x over n. But in 96 on the left-hand side, if I ignore the omega n term, I have minus f of the largest second of the smallest prime factor. So the two minuses will give me a plus x over phi of k in 97, and that will cancel the x over phi of k in 96. So the main terms cancel. So this miraculous cancellation leads to this being equal to little o of x. We already know the fractional part is little o of x, and now we add and we get x times this is little o of x, and now we divide by x, and then now we get our result that this sum from 2 to infinity of mu n omega n with p of n L mod k is little o of x. So that is the proof. So this involves a whole bunch of things, combination of my earlier work together with the prime number theorem for arithmetic progressions. Okay, I'll now skip this section, and I will say something about first order duality for general f. So the way the first order duality for general f was proved was I actually showed that summation mu of n f for the smallest prime factor of n is little o of x. Axer then showed with the fractional part. Then with the integral part, I got this f of p of n. So now if you assume that this f has an average c, then you end up showing by adding those two that this has got minus c. That's exactly how I proved it there. Now let us try to do the same game for m omega. So now we're going to look at this function mf of x, which is the sum of the mu of n omega n f of p of n. This is recent work with my PhD student Yazan Alamudi, where the paper is not completed, but anyway, we can show this result that this is little o of x. By Axer's method, we get fractional part. Now at this point, you will say, this is the same story. No, it's not. Because when I go with the duality, I end up getting this identity with omega n minus 1. With that identity, you get the average of the second largest prime factor. Remember, previously, without the omega n, I had the largest prime factor. So, really speaking, what we end up getting is the difference between the average of f over the second largest prime factor and the average of f over the largest prime factor. Previously, I took f to be the characteristic function of primes in an arithmetic progression, and I showed that the largest prime factor is uniformly distributed. The second largest prime factor is also uniformly distributed, so the two averages are the same. That's the cancellation I got. But for a general function f, where is the guarantee that the two averages are the same? So the theorem I'm going to state is, if f is a bounded function on the primes, such that on the largest prime factor we have an average kappa, and on the second largest prime factor we have the same average kappa, then this sum has value 0. And now the problem I ask is, does there exist a bounded function f on the primes which has two different averages, one on the largest prime factor and one on the second largest? I don't think such a function exists, but I don't have a proof that this is the case. Okay, so this is an interesting problem. Okay, and finally, I want to talk about algebraic analogs. So there is this well-known, very beautiful theorem called the Shabatarov density theorem in algebraic number theory. And Madeline Locus-Darcy, a former PhD student of Ken Ono, actually at Ken Ono's suggestion, extended my result to algebraic number fields as follows. She now considers a Galois extension K of the base field Q of rationals. And so let G be the Galois group. And you take a conjugacy class in this Galois group. Now you take the summation mu of n over n less than or equal to 2, such that the K over Q is in this conjugacy class, right? But now we are looking at the opt-in symbol, but I'm sorry, I should have put in a second largest prime factor condition here. So when you put the second largest prime factor condition, this turns out with this will now give you minus C over G. What Darcy says is, and this is a good observation, that if you take G to be a cyclotomic extension of G, K to be a cyclotomic extension of G, then the Galois group is abelian, and therefore the conjugacy classes are all of size 1, which means this minus C over G is now minus 1 over phi of K. So my results follow from this if you, in the case of a cyclotomic extension. So this is Darcy's result. Now, I use the strong form of the prime number theorem. And so what Darcy uses is she uses the Shabatarov density theorem in strong form due to Legarius and Odlyzko. Okay, but now I make a comment. Essentially, what Darcy does is she takes the sequence of largest prime factors and shows that for the largest prime factors, if I do the Shabatarov, if I use the conjugacy class defined in terms of the largest prime factor, then you get C over the size of C over the size of G. But that means the little c in my general theorem is now established as capital C over G in Darcy's theorem. And therefore, the Mobius series, which will converge to minus C in my theorem, converges to this. So in one sense, Darcy's result follows from my general result when applied to this algebraic situation. However, my general result has no specific error term, whereas Darcy is able to get an explicit error term because she uses the Shabatarov density theorem. So this has been further generalized by Sweeting and Wu, where instead of a Galois extension of Q, they consider a Galois extension L of an arbitrary algebraic number field K. And later also has been extended to the situation, I think Wang has extended it to global function fields. And there is also a paper, I think it is by Wang, who has done it by replacing the Mobius function by the Ramanujan sum. So this is a Ramanujan lecture. So anyway, I bring back Ramanujan here. So we all know that the Ramanujan sum written down here at m equal to 1 is the Mobius function. So there is also another result in that direction. And now more recently, by the way, Ono, along with Schneider and Wagner, has written actually 2 papers where they interpret this 1 over phi of K in terms of arithmetic densities, and then they discuss Q analogs of this. So some of you who are listening to this talk who come from the world of Q would be interested in reading that paper. Finally, I have to mention here that my other PhD student, Sengupta, has taken the Alladi-Johnson results on mu and omega n, and he has obtained exact analogs of these in algebraic number fields, K being Galois extension of Q, of the results of Darcy. But now he has to do the same analysis with the second largest prime factor, and we are now working on the kth largest prime factor. So here are these references. My joint work with Alamudi in preparation, my joint work with Sengupta on higher order dualities in preparation, the work of Darcy and Wang. There is this important paper of Legarius and Odlyzko on the effective version of the Shabatarov density theorem, Ono, Schneider, and Wagner on the Q analogs, and Sengupta has just submitted his paper to the archives on the algebraic analogs of the Alladi-Johnson results. And so with that, I'd like to stop and open up the floor for any questions or comments. Thank you again.
Thank you.
So do you want me to stop sharing, or what do you want me to do?
I think we can have it in case somebody wants to go back.
Yeah, sure. Okay, go ahead.
Thanks for the wonderful talk. Are there any questions for Professor Alladi? Yeah, Sagar wants to ask a question.
Sure.
Professor, that was an amazing talk. I had a few
Thank
questions. Firstly, regarding the generalization which you are doing in the algebraic setting. So over
Yes.
there, how are you fixing the largest prime? I mean, what ordering
Yeah, yeah,
is being
yeah.
used for that?
So that is why that is, so, okay. Sorry. Hold on. It's missing in the slide, okay? It's there in here. So it is not, so when we go back to the symbol.
Yeah.
So there is the largest prime factor coming in at the bottom. It is the Artin symbol of K over Q with regard of P of n. Must be C.
Okay.
Okay. The Artin symbol is this Frobenius map. So it is given in terms of that Frobenius. Yeah. So that's where the P of n must come in.
All right. So it's
So
not
it's there, it
going
is
to be
there.
total order. It is something which would be a very specific order going on some
Going with
proper
correct.
subfield.
Correct. So,
So
the
my other
mistake,
question was
the mistake
regarding the
is here.
philosophy.
Yeah, the mistake is here. Here I should have put P of n instead of that. Okay.
Okay.
It's there. It's corrected in the bottom. Yes.
Okay. So my other question was with regards to how this proof has gone. So if we are looking at the largest prime divisor or the second largest prime divisor, that is uniformly distributed mod k, right?
Correct.
But now, I mean, I was just thinking that the smallest prime divisor would never be uniformly distributed.
Absolutely.
So now, I mean, since we are having a result that the largest and the second largest are both uniformly distributed, I mean, thinking about it, if one is just going from the top, like third largest, fourth largest, at
Yes.
some point of time, there should be a breakdown where uniform distribution goes to non-uniform. So
No. So yeah, you are right, but it's not like that. We are fixing the K.
Yeah, we are fixing the K, but still, I mean.
Now let's put it. Let's not use K. So let us say we take the jth largest prime factor. We are fixing the J. So for each fixed J, the sequence of jth largest prime factor is uniformly distributed modulo K.
Yeah, so it would be, so going from the top, going from the jth largest, it would always be uniformly distributed. That is how we should be expecting the result, right?
Correct. And we only look at integers which have at least J prime factors.
All right. Yeah, then that makes sense.
Yeah, and so that is why there is a point at this proof where I say we only look at integers where omega n is bigger than or equal to 2. The number of integers with omega n equal to 1 is the primes, x over log x. So the number of integers which have got no more than j minus 1 prime factors, while Lado's result is no more than x log x to the j minus 2 over j minus 2 factorial log x.
Yeah.
So that's small in comparison.
Yeah, so that would make it to be a negligible set in this setting. Yeah.
Correct.
Thank you for that.
Yeah. Okay.
Any other questions? So I had one question. So towards the end, you had talked about the results being generalized for Ramanujan sums. So,
yes.
Who has done that?
Okay. I think it's, let's go to the references. I think it's Wang. The Ramanujan sum and Shevatar of density. It appeared in the Ramanujan Journal 2021.
Okay. So how does the summation mu of n over n equal to 0 get generalized to? I mean, is there a corresponding result to the Ramanujan sum?
Yes. Actually, he did it in, I think Wang also has replaced mu of n by lambda at Liouville.
Oh.
Okay. All right. And then he replaced the mu of n by the Ramanujan sum. Okay. And he uses, of course, the multiplicative property of the Ramanujan sum, like the multiplicative property of the Mobius function. Take a look at the paper. I mean, it'll come through very nicely.
Oh, okay.
Now, these things have not been done with omega.
Oh.
They've only been done for mu of n, not for mu of n omega n.
Okay.
Okay. So these results that I am stating, all the sweeting Wu and everything else, that is from the original setting, mu of n over n, smallest prime factor L mod k.
Yeah.
The recent one with mu of n omega n is mine with Johnson, then Alladi Alamudi, and then Sengupta's paper, and my paper with Sengupta. So that's where we stand currently.
So with Sengupta, it is also done in the algebraic setting, right?
Yeah. Is Sengupta also not just algebraic? It's done in the algebraic setting of a Galois extension of Q.
Okay.
That was the original paper of Dawsey.
Okay.
Right. So in Sweeting and Wu, when they did the more general, L being a Galois extension of K, some general number field, they had to define the analogs of the Mobius function there. So the way they do it is they look at ideals and break it up into prime ideals and then -1 to the number of, things like that they have to define. And then they do a duality there. And then they apply all that.
Okay.
For K over Q, it's easy because the base field is Q.
Hmm.
I'm not saying easy. It comes out from the standard thing because the base field is Q. Yeah, I shouldn't use the word easy.
Right.
Okay. So, but for L over K, you have to develop the machinery there. And now, of course, Sengupta is also working on this, but yeah, so but the L over K for the mu and omega n has not been done.
Okay, right. So I think Sagar has one more question.
Yes.
So Professor, I was thinking that is it possible for us to get a duality for the second largest prime as well?
You mean like
So,
connecting second smallest to second largest?
yeah, something like that.
I don't know. I mean, what naturally comes out is so let me go back to the very first slide. So what naturally comes out is that if you put the weight as the Mobius function, right? Oops, I'm able to move this. So let me just move this slowly like this. Okay, so if I just write down Mobius function f for the kth largest, you don't get the kth smallest. I mean, you actually get only the smallest, but with the weight.
Oh.
So that's how you get it. Maybe if you do something else, you may get, I don't know. Maybe you have to replace the Mobius function with some other function. Maybe then you may get it.
Yeah.
This is duality. And where do I have the second order duality? I think I have it here. Yes.
Yeah.
So, I mean, that's what I automatically tried was mu with the kth largest and the kth smallest. And then I ended up getting only the smallest prime factor and the largest. So it's not a duality between the kth largest and the kth.
Okay, so that would be just the weight thing, right? Okay,
Yeah,
thank you, Professor.
And I think one of the reasons this was not investigated is that mu of n is multiplicative and omega n is additive. So when I wrote to Tenenbaum, he said, and I wrote about my results, he said, well, first of all, this combination of multiplicative and additive has not been discussed before, but you can get it via Selberg-Delange. So it's very interesting. Delange has this observation on log, but nobody applied it to this problem. So this is something I always tell my students, right? You may have very general results, but one may miss striking special cases. And, because so in the desire or in the effort, I would put to do these general results, we may miss some very interesting and important aspects of certain special cases.
Okay.
Yeah.
Thank you.
Okay.
Okay, if there are no further questions, let's thank Professor Alladi again.
So let me first close this. How do I stop sharing? Oh, here. Somewhere I must go to stop share, right? Yes, I'll stop sharing, and now I think I can see everybody. Yeah. So yeah, thank you very much.
Yeah, thank you for the wonderful talk. Yeah.
You're welcome. So first of all, how long has this seminar been going on?
I guess
3 years?
3 years.
No, it's
3
more
years.
than
Okay.
that, right? During COVID.
During COVID, it started.
Oh, I see. You started at that time. Yeah. That's when the big Zoom thing began.
Yeah.
During COVID.
So
Well,
I
actually, it has turned out to be quite useful. Yeah.
I just want to tell the students here that if the best they can do right now about getting an ADOSH number is to collaborate with you, and then they can get to 2.
We have lower ADOSH number.
So yeah, so this could be a impetus to solve some of the problems and
Right. And there are some other things which I didn't mention in this. There's a beautiful paper of Terry Tao and so on, and I'm working on that with another student. So yeah, so next talk maybe on this topic, not just this seminar, elsewhere maybe will involve all of those things.
Thanks.
Okay.
Yeah.